Hi, welcome back to Moose and Chemistry. This is electron configuration of the element copper. Now, when we look on the periodic table, copper happens to be the element number 29, right? So that means the atomic number is going to be 29. So let's write a 29 right here. All right, and when we look at the atomic mass unit, it's going to be roughly 64. All right, so it has 29 protons, 29 electrons. And now, what about the number of neutrons? Well, remember that we do AMU minus protons to give us neutrons. So when we do that, that's going to be 64 minus 29 equals 35. Pretty darn snarly. So we're going to have 35 neutrons. So let's go ahead and erase some of this to give us some more space. Excellent. So back to the old drawing board, let's say. Now, let's look at the electron configuration. Now, before we start that, we have to remember that the S subshell can hold 2 electrons, the P subshell can hold 6 electrons, the D subshell can hold 10 electrons, and the F subshell, wow, that one holds 14 electrons. So we're going to use something called the Aufbau principle, which says you have to fill the lower shells first before you fill the upper shells. But we're going to be doing it using the diagonal rule. Pretty darn snarly, eh? Yes. So now, let's go ahead and let's get it started. So 1s2, 2s2, and remember we got to fill up 29 electrons, huh? 2p6, 3s2, 3p6. Now, we're going to have to be careful here because this is the 9th element over and the 3rd energy level of the D block, which means that, remember, Hund's rule says that you have to fill all the suborbits, the lower suborbits first, the up arrow, right? However, we're only one away from filling that, so we're not going to put a 4s2 here. We're going to put a 4s1. And then we're going to make 3d10. Now, let me show you something. The biggest mistake that people make is they call this 4s2 3d9, right? That's a huge mistake. Because you see, remember that the D shell can hold 10 electrons, right? And the D shell, this 3d, according to Aufbau principle, is actually lower than the 4s. Why do we fill the 4s in first? Because it only has 2 electrons, it's easier to fill. So what you really have to do is this. When you're one away from completing the shell, or if you were halfway, like in the element, let's say chromium, you have to take one off that 4s and give it to the D and make that 3d10, that 4s1. Again, these are exceptions, so you have to watch out for these guys. So let me go ahead and take care of that and erase that real quickly. All right, just remember those exceptions, because they're out there. All right, now, we're going to do a Hund's rule next. So here we go. Up arrow and then down arrow. Again, up arrow and then down arrow. Here's a perfect example of Hund's rule that's clearly able to be seen. You got 2px, 2py, 2pc. Now watch this. Up, up, up. We filled every subshell with an up arrow first before we start the down arrows. Down. Then 3s up and down. Same thing with 3px, 3py, 3pz. Look. Up, up, up. Then down, down, and down. Remember, the 4s is only going to get 1, so that's up. Now watch this. 1, 2, 3, 4, 5. So that's 3dx squared minus y squared, 3dxy, 3dyz, 3dxz, 3dz squared. Now we're going to fill in the down arrows. 1, 2, 5. Pretty snarly, huh? You've got to be careful of these exceptions because they are out there. All right, now what's the nearest noble gas to copper? Well, argon, of course. So we're going to put argon in there. And then we're going to take our valence shell right here. love neon shell. And this time we're going to write it numerically in order. So we're going to go 3D10, 4S1. Pretty darn cool, huh? Now, let's look at our quantum notation. Now, when we get ready to put the principal quantum number in there, you might be tempted to write 4. But look carefully. It's in the D block, right? Copper's right about here in the D block. So it'd be N minus 1. So you would go 4 minus 1, which would give us 3. So our principal quantum number is 3. Now, our angular momentum quantum number, since it's a D block, is still 2, so that goes there. Now the magnetic number, you have to repeat this pattern. So it's minus 2, minus 1, 0, 1, 2. That's 5, minus 2 is 6, minus 1 would be 7, 0 would be 8, and number 1 again would be 9. It's just a ninth element over in that. So we put a 1 there. Now, let's look at the last arrow in our shell here. So think about this. People would be saying, oh, that 4S, that's the last arrow. No, it's not. That's not the last arrow. Do not call that as the last arrow. The last arrow is actually right here. That's your last arrow. So you're going to have 1/2 negative. And now we've fulfilled the Pauli's exclusionary principle, which says that no two elements can have the same set of quantum numbers. Pretty darn snarly, huh? Well, you guys be awesome, and we'll see you back here at Moosing Chemistry.